Covalent bonding. So the Lewis structures are going to show molecular compounds as being neighboring atoms which are sharing electrons to attain octets. So let's use Lewis structures to show bonding in water and chlorine. And we're going to identify bonding pairs and lone pairs. And I put those things there to tell myself what to do. So here's water. There's 2 hydrogens and an oxygen. And how many electrons does hydrogen have? 1. That was supposed to be a gimme question. How many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. It has 2 plus 4. I should have done these in different colors. I'm going to do these in different colors. Because I have colors, I might as well use them, right?
Are we going to have to make our own?
Your own colors?
No, I'm saying, can we use like stars or dots or triangles?
You have to use dots. Okay, so here's oxygen. Oxygen has 6 valence electrons. Is oxygen happy? No. Oxygen wants 8. Is hydrogen happy? No. How many valence electrons does hydrogen want? 2. He just wants to be like that littlest noble gas, helium. So the oxygen is trying to convince hydrogen to give her one of its electrons. And he says no. And the hydrogen is trying to convince oxygen to give him one of her electrons. And she says no. Nobody's willing to give up an electron. So they decide to share. So hydrogen is sharing its electron with oxygen. Oxygen is sharing its electron with hydrogen. And this is going to happen over on this other side as well. And then oxygen's here in the middle. And so oxygen is counting all of these electrons as belonging to her. 2, 4, 6, 8. Oxygen's happy. Hydrogen's happy because he's got 2 electrons here. And hydrogen's happy because he has 2 electrons here. The shared electrons count for both. Dr. K and I have 6 children. If you ask him how many children he has, he'll say 6. If you ask me, I'll say 6. Are there 12 children in our house? No, there are not. At times they are, but they're not ours. So there are 6, but they count twice because they're mine and they're his. They're shared, right? So we've like multiplied our efforts here by sharing. Sharing is a good thing. And so they've both got octets. So in this structure here, which electrons are bonding pairs? It'd be these guys, the ones that are shared, right? And which ones are not being shared? These 2 and these 2, right? So those are the lone pairs, and the green ones are the bonding pairs. Bonding pairs are electrons that are shared between, and lone pairs are the ones that are not. It's kind of, well, it doesn't work. It doesn't work so well anyway. I'm just not, stay away from that analogy. Just stay away. Any questions about water? Let's do chlorine. So there's chlorine. How many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. And then I'll draw another chlorine, and I'll use a different color just so we can see what we've got. And that one also has 7. 1, 2, 3, 4, 5, 6, 7. Now, those guys could be happy. Ooh, wrong thing. They can be happy by sharing each sharing one electron with the other. So here's the bonding pair right in the middle. And then how many lone pairs are there? There's a lot. There's 3 on each chlorine. All of those are lone pairs. It's important to be able to identify bonding pairs and lone pairs. Any questions? You can share more than one electron pair. See, my husband and I have a triple bond, right? We have 6. It's a triple bond. Let's look at the double bond first. So oxygen. So there's one oxygen, here's another oxygen. And each of these guys has 6 electrons. So they need to share. I'm just going to connect the dots this time. I'm going to say, well, if they share that one, that pair, then we're getting better, right? But that's not going to take care of the problem. So what if they share another pair of electrons? So I'm going to draw that over here. This is a double bond. 2 pairs of electrons. Single bond, 1 pair of electrons. Double bond, 2 pairs of electrons. Guess what a triple bond is? 3 pairs of electrons. And so you'll often see that as just 2 lines. And then it's important to remember that the line represents 2 electrons. So it's like 2 electrons and you connected the dots. It's just the dots are small and you can't see them up there anymore. So these are 3 different ways. This is the neatest and this is the messiest. Let's look at nitrogen. Dang. Nitrogen. How many valence electrons? Okay, it's got 5. So N2, they can share that pair, and then they'll have to share this pair and this pair. So this nitrogen counts 2, 4, 6, 8, and this one counts 2, 4, 6, 8. There's a lot of counting by 2s to 8 when you're doing this. Did you break your chair? No. That's good. It was already broken. So let's look at how this helps us to understand reality. So this model predicts that water is stable and that H3O is unstable. And this is true. It also predicts H3O plus and H2O2. Let's look at H3O. H3O. Oh, that's just, I'm going to start over because that was not going well at all. Just zoom in a little more. Okay, so here's oxygen. And let's use a different color here. Green maybe. I'm fighting here. Okay, so here's hydrogen. And here's another hydrogen. And so we'll get a bond there and a bond there. And then what's going to happen if we bring in another hydrogen? Is that oxygen in good shape? No. No, it isn't. It's got too many electrons. H3O is not a stable molecule. What about H3O plus? Making this a positive ion What would that do to the number of electrons?
Take one.
It would take one away. So we could get rid of that one. Now are we okay? Now we're okay. H3O plus is stable. H3O is not. So looking at Lewis structures of molecules helps us to predict stability. We really need to put brackets around this guy and put a charge on the outside, otherwise he has around 100 electrons. Covalent bonds are highly directional, unlike ionic bonds. In sodium chloride, you have sodium and chloride, and they are attracted in multiple directions to their neighbors. These covalent bonds are between two particular atoms, and there is no attraction away from that. So we find that covalent molecules have discrete molecules. That didn't make any sense. Covalent compounds have discrete molecules, and that there are very weak forces between the molecules, and so covalent compounds tend to have much lower melting points than ionic compounds. Ionic compounds have these attractions in 3 dimensions, and so they melt at much higher temperatures.